An AI system can work exactly as designed and still create outcomes no one actually wants. The problem is not always that the model fails. Sometimes it succeeds too well, optimizing a goal so precisely that it exposes a deeper mistake. The goal itself was too narrow. Consider a recommendation algorithm designed to maximize user engagement. It tracks watch time, clicks, shares, and interaction patterns. Over time, it becomes highly effective at predicting what keeps people on the platform longer. From a technical perspective, this is success. But maximizing engagement does not necessarily maximize well being, information quality, or social trust. If the system promotes emotionally charged or polarizing content because it drives interaction, it is not malfunctioning. It is optimizing the metric it was given. The objective was clear. The outcome is more complicated. This pattern appears in many domains. In logistics, an AI model may optimize for cost efficiency by reducing delivery times and minimizing inventory buffers. The system becomes lean and highly efficient. But if unexpected disruptions occur, the lack of slack can make the network fragile. Efficiency was optimized. Resilience was not. In hiring, a model may optimize for candidates who resemble past high performers. If historical success correlates with specific backgrounds, the system may consistently favor similar profiles. Performance is optimized. Diversity or long-term adaptability may not be. Optimization requires definition. Every AI system is built around an objective function, a formal description of what the model should maximize or minimize. That objective is necessarily a simplification of reality. Real-world goals are multidimensional. Profit, fairness, safety, trust, and sustainability rarely align perfectly. To make optimization possible, designers select measurable proxies. Once defined, the system improves relentlessly along that axis. The narrower the definition, the sharper the optimization. There is a strong counterargument. Without clear objectives, systems cannot function effectively. Businesses need measurable targets. Models require quantifiable criteria to learn. If engagement, cost, or accuracy can be measured, optimizing them can produce tangible benefits. In many cases, it does. Medical diagnostic systems that optimize detection rates can identify conditions earlier. Fraud detection models that optimize anomaly detection can reduce financial loss. Optimization is not inherently flawed. The challenge lies in mistaking a proxy for the whole. When a metric becomes the target, behavior adapts around it. This dynamic is sometimes described in economic theory. Once a measure becomes a goal, it can lose its value as a measure. If customer service teams are evaluated primarily on response speed, interactions may become shorter but less thorough. If teachers are evaluated strictly on standardized test performance, instruction may narrow to test preparation. When AI systems optimize these metrics at scale, the effect intensifies. The system is not misaligned with its instructions. It is aligned with a simplified instruction. Second-order effects often emerge slowly. A recommendation system that optimizes for engagement may reshape content production incentives. Creators adjust to what performs well. Formats converge. A pricing algorithm that optimizes for short-term revenue may influence long-term brand perception. A predictive maintenance model that minimizes downtime might inadvertently reduce opportunities for human skill development. The first-order outcome looks positive. The broader ecosystem shifts quietly. Another complication is feedback loops. When optimized systems influence the data they later train on, narrow objectives can reinforce themselves. If a hiring model consistently selects similar candidates, the performance data used to retrain the model reflects that selection. The optimization appears validated. Divergent paths become less visible. Over time, the system's definition of success can become self-reinforcing. This does not mean AI designers are careless. Defining objectives in complex systems is inherently difficult. Trade-offs must be made. Constraints exist. Perfectly capturing every dimension of a goal is rarely possible. But as AI systems become more capable, the consequences of narrow definitions become more pronounced. The more efficiently a system optimizes, the more clearly its blind spots appear. Organizations are beginning to recognize this. Some incorporate multi-objective optimization. balancing efficiency with fairness or robustness. Others implement human review layers to catch unintended effects. These approaches can mitigate risks, yet they also introduce complexity. Balancing competing goals is harder than optimizing a single metric. There is no simple formula for alignment in messy environments. The deeper lesson is structural. AI systems amplify whatever objective they are given. If that objective is incomplete, the amplification will reveal the gaps. The technology does not decide what matters, it executes what is defined. That distinction shifts responsibility back to institutions and designers. As automation spreads into more areas of decision making, clarity about objectives becomes increasingly important. The question is not only whether a system works, it is whether it works toward the right definition of success. When AI optimizes the wrong thing perfectly, the failure is not in the code, it is in the framing. Recognizing that does not diminish the value of optimization. It simply reminds us that in complex systems, defining the goal is often harder and more consequential than achieving it.